Hello, friend, and welcome back to Science for Sleep. Tonight, we'll rest together inside one of the most familiar and least observed parts of everyday life, the brain. Not as a place where thoughts live, and not as a control center issuing commands, but as a living system that continues quietly, moment by moment, whether it is noticed or not. This is not an exploration that asks for focus or effort. It is a gentle unfolding, meant to move slowly enough that curiosity can remain calm as the night deepens. In science, the brain is not defined by ideas or identity, but by activity. It is a network of cells exchanging signals, adjusting relationships, and maintaining balance across time. Even in stillness, even in rest, this activity does not pause. The brain is always in motion, not rushing, not striving, simply continuing its patterns in response to internal and external conditions. Understanding this does not require holding on to details. It only asks that the pace of thought soften as information settles. Rather than asking what the brain produces, science often asks how it sustains itself, how energy flows through networks, how signals travel and return, how stability is preserved even as change continues. From this perspective, the brain is less like a container and more like a process, one that unfolds gradually, shaped by history, environment, and time. There is no single location where experience resides, and no single moment where meaning is stored. Everything emerges through coordination. Throughout this video, we'll explore how the brain communicates, how it adapts, and how it maintains continuity without supervision. We'll look at patterns that repeat, systems that regulate themselves, and rhythms that persist across years and decades. The goal is not explanation for its own sake, but gentle clarity, the kind that allows the mind to loosen rather than tighten. If you enjoy these quiet journeys through science, you're welcome to subscribe. And if you feel comfortable, you can leave a comment sharing where you're listening from tonight. It helps others find their way to this calm space, one listener at a time. For now, there is nothing you need to remember and nothing you need to follow closely. The information will move at its own pace. The brain does not require attention in order to function. It does not ask to be observed or understood to continue its work. As the night goes on, we'll explore how this system organizes itself without awareness, how it balances change and stability, and how it supports continuity across time. For now, you can allow the pace to slow further, letting the idea of the brain rest not as an object to examine, but as an ongoing process unfolding quietly in the background, steady and unhurried as the night continues. From a scientific perspective, the brain is not defined by thoughts, decisions, or awareness. It is defined by structure, activity, and relationship. At its most basic level, the brain is a collection of living cells organized into networks that exchange signals continuously. These signals move through space and time, forming patterns that shift moment by moment. What we call thinking or perception emerges from these patterns. But the patterns themselves exist independently of attention. The brain is made primarily of specialized cells called neurons, supported by other cells that provide structure, energy, and protection. Neurons are not passive carriers of information. They are active participants in communication, responding to changes in their environment and adjusting how they signal over time. Each neuron forms connections with many others, creating pathways that allow signals to travel across wide regions. The brain's function arises not from individual cells, but from how these connections work together. Importantly, the brain does not operate as a single unit. There is no central node where all information arrives or departs. Instead, activity is distributed across many regions simultaneously. Signals move in parallel, overlap, and influence one another. This distributed organization allows the brain to remain flexible and resilient. When one pathway changes, others adjust, preserving overall balance rather than collapsing into failure. Energy plays a constant role in this process. The brain consumes a steady supply of energy to maintain signaling, repair cellular components, and regulate its internal environment. Even during rest, energy use remains high. This ongoing demand reflects the fact that the brain is always active, maintaining readiness and coordination, rather than switching on and off. The brain also exists in continuous relationship with the rest of the body. Signals flow inward from sensory systems and outward to organs and muscles, forming feedback loops that help regulate temperature, breathing, heart rate, and movement. These exchanges do not require conscious oversight. They occur automatically, guided by patterns that have been refined over long periods of time. From this viewpoint, the brain is less an object to be located and more a process to be understood. It is not a static structure waiting to be used, but a living system that is always in motion. Even when the mind is quiet, the brain continues to coordinate, adjust, and maintain balance. Understanding what the brain actually is helps remove the sense that it must be monitored or controlled. It functions through interaction rather than command, through regulation rather than instruction. The patterns continue whether they are named or noticed. As this foundation settles, attention can move gently toward how this living system sustains itself. The next step in this exploration lies in understanding the brain as a dynamic process, one that maintains continuity through constant change, quietly adapting as time moves forward. The brain can be understood most clearly when it is viewed as a living system rather than a fixed structure. Living systems are defined not by stillness, but by ongoing activity. They maintain themselves through continuous exchange, adjusting to internal and external conditions in ways that preserve balance over time. The brain follows this same principle, remaining active and responsive even when the body is at rest. At every moment, countless processes are unfolding within the brain. Cells regulate their internal environments, repair small amounts of damage, and adjust how they respond to incoming signals. These changes are not dramatic or sudden. They occur gradually, layered one upon another, creating continuity rather than disruption. The brain survives not by resisting change, but by incorporating it. One defining feature of a living system is self-regulation. The brain does not rely on a single command signal to maintain order. Instead, it uses feedback. When activity increases in one area, signals elsewhere adjust in response. When resources are used, replenishment follows. When conditions shift, relationships between networks adapt. This constant adjustment allows the system to remain stable without becoming rigid. Time plays an essential role in this process. The brain operates across multiple timescales simultaneously. Some signals last only milliseconds, while others reflect patterns shaped over years or decades. These layers of time coexist, allowing rapid responses to occur within a framework of long-term continuity. The brain's ability to integrate across these scales is what allows learning, adaptation, and persistence to happen together. Energy flow is another hallmark of living systems. The brain continuously converts energy into activity, using it to maintain communication and structural integrity. This energy use is not directed toward a single goal. It supports the system as a whole, ensuring that signaling remains possible and that internal conditions stay within workable ranges. Even in quiet states, this energy flow does not stop. Living systems are also shaped by history. The brain reflects past activity in the strength and organization of its connections. Experiences do not disappear when they end. They leave subtle traces that influence future responses. This does not mean the brain stores events as fixed records. Instead, it adjusts probabilities, making some patterns more likely and others less so, based on what has come before. Importantly, a living system does not need to be observed to function. The brain does not require attention or awareness to regulate itself. The mind may drift, focus, or fade, but regulation continues uninterrupted. The processes that sustain the brain operate beneath awareness, guided by relationships rather than intention. Viewing the brain as a living system shifts emphasis away from control and toward coordination. It becomes clear that stability arises from interaction, not from dominance of one part over another. The brain maintains itself by responding, adjusting, and continuing, moment by moment. As this understanding settles, attention can move gently toward the components that allow this system to communicate internally. The next step in this exploration lies in examining how neurons exchange signals and how this communication forms the basis for the brain's ongoing activity, quietly shaping experience without requiring effort or direction. At the foundation of the brain's activity lies communication. The brain does not function through isolated parts acting alone, but through constant exchange between cells. Neurons are the primary cells responsible for this exchange. Each neuron is a living unit, capable of receiving signals, responding to them, and passing information onward in ways that change subtly over time. Neurons communicate using a combination of electrical and chemical signals. When a neuron becomes active, small electrical changes travel along its structure. These changes do not represent messages in the everyday sense. They are shifts in charge that influence whether the neuron will pass activity forward. This electrical signaling allows information to move quickly across distances within the brain. At the points where neurons connect, communication becomes chemical. Neurons do not touch directly. Instead, they are separated by tiny gaps known as synapses. When an electrical signal reaches a synapse, it triggers the release of chemical messengers. These messengers cross the gap and influence the activity of the next neuron, increasing or decreasing the likelihood that it will become active. Communication, in this sense, is probabilistic rather than guaranteed. Each neuron forms connections with many others, sometimes thousands. These connections are not fixed. Their strength can change based on how often they are used and under what conditions. Some pathways become more efficient over time, while others weaken. This ongoing adjustment allows communication patterns to reflect experience without storing it in a rigid form. Importantly, neurons do not send signals in isolation. Activity spreads across networks, with many neurons participating simultaneously. The meaning of a signal lies not in a single neuron's activity, but in patterns that emerge across groups of cells. These patterns shift constantly, forming and dissolving as conditions change. What the mind experiences as continuity arises from this coordinated motion, rather than from static representation. Neural communication is also shaped by context. Chemical conditions within the brain influence how easily signals spread and how strongly connections respond. This means the same input can lead to different outcomes depending on timing, internal state, and recent activity. Communication is flexible, allowing the brain to adapt without requiring explicit instructions. Despite the complexity of this system, it operates quietly and efficiently. Signals flow, connections adjust, and patterns reorganize without awareness. There is no central observer coordinating the exchange. Regulation emerges from the interactions themselves, guided by feedback rather than command. Understanding neurons and communication reveals how the brain maintains activity without becoming chaotic. The balance between electrical speed and chemical modulation allows information to move while remaining adaptable. This balance supports stability across time, even as individual signals come and go. As this picture settles, attention can move gently toward how these individual exchanges scale up into larger patterns. The next step in this exploration lies in examining how neurons form networks and how these networks give rise to coordinated activity across the brain, quietly shaping function without requiring a central control point. Although the brain is often described in terms of regions and areas, its activity does not arise from isolated centers acting alone. Instead, function emerges from networks of neurons working together across wide distances. These networks are not fixed circuits with single purposes. They are flexible patterns of coordination that form, dissolve, and reform depending on context and need. A network is created when groups of neurons begin to influence one another's activity over time. Some connections are local, linking nearby cells, while others span distant parts of the brain. Together, these connections allow information to be shared across systems that handle sensation, movement, memory, and regulation. No single location contains a complete function. What the mind experiences as a unified process arises from distributed interaction. This network-based organization adds resilience. When activity in one area changes, other parts of the network can adjust, preserving overall coordination. Rather than relying on a single point of control, the brain spreads responsibility across many interacting elements. This distribution allows the system to adapt smoothly to variation, maintaining balance even when conditions shift. Networks are also dynamic. They do not remain active continuously. Instead, different networks become more or less prominent depending on internal and external conditions. During focused activity, certain networks strengthen their coordination. During rest, other patterns become more active. These shifts do not require instruction. They emerge naturally as signals flow, and feedback adjusts relationships. Importantly, the same neuron can participate in multiple networks at different times. There is no strict assignment of cells to single roles. This flexibility allows the brain to reuse its components efficiently, supporting a wide range of functions without duplicating structure. Networks overlap, share resources, and influence one another, creating a layered organization rather than a hierarchy. Scientists study networks because they reveal how large-scale coordination is achieved without central oversight. Activity spreads through interaction rather than command, guided by probabilities and timing rather than fixed rules. This approach helps explain how the brain remains coherent despite constant change. Understanding the brain as a collection of networks rather than centers helps remove the idea that any single part must be monitored or optimized. The system functions through relationship. Stability arises from cooperation, not control. As this understanding settles, attention can move gently toward another layer of organization. Beyond networks themselves, the brain's activity unfolds in rhythms. The next step in this exploration lies in examining how electrical patterns coordinate networks over time, forming the background structure that supports ongoing communication. Beneath the visible structure of networks lies a quieter layer of organization, the rhythmic electrical activity that coordinates communication across the brain. This activity is not a signal to be interpreted, but a pattern to be maintained. Electrical rhythms emerge naturally as neurons exchange signals, rising and falling as groups of cells become active together and then settle again. When scientists measure this activity, they observe repeating patterns often referred to as brain waves. These patterns are not waves moving through space, but synchronized changes in electrical activity across populations of neurons. Different rhythms reflect different modes of coordination, allowing networks to align their timing even when they are physically distant. Rhythm, in this sense, supports cooperation rather than instruction. Electrical activity changes continuously. Faster rhythms tend to appear when communication needs to be flexible and responsive, while slower rhythms are associated with stability and integration. The brain does not choose these rhythms deliberately. They emerge as a result of how neurons interact under specific conditions, shaped by chemistry, connectivity, and recent activity. Importantly, multiple rhythms can exist at the same time. Different regions may coordinate at different speeds, allowing parallel processes to unfold without interference. These layered rhythms allow the brain to manage complexity without becoming chaotic. Timing becomes a shared reference, helping networks exchange information efficiently. Electrical patterns also help regulate transitions between states. Shifts in rhythm often accompany changes in attention, rest, or sleep. These transitions do not happen abruptly. Rhythms adjust gradually, preparing networks for new modes of operation. This smooth adjustment supports continuity, allowing the brain to move between states without disruption. The presence of rhythm does not imply control or command. No single region sets the pace for the entire brain. Instead, rhythms arise from mutual influence, with networks adjusting to one another through feedback. Coordination emerges from relationship rather than hierarchy. From the perspective of the mind, these rhythms are not experienced directly. They operate beneath awareness, shaping timing and flow without announcing themselves. Their role is supportive, not expressive, providing a background structure that allows communication to remain organized. Understanding electrical activity as rhythm rather than message helps clarify its function. It is less about carrying information and more about creating conditions where information can move smoothly from one part of the brain to another. As this idea settles, attention can move gently toward the chemical side of communication. Electrical rhythms provide timing, but chemistry shapes probability. The next step in this exploration lies in understanding how chemical signaling influences brain activity, quietly modulating how networks respond over time. Alongside electrical activity, chemical signaling shapes how communication unfolds within the brain. While electrical signals move quickly and define timing, chemical messengers influence likelihood and tone. They do not command neurons to act. Instead, they adjust how responsive networks are, gently shifting the probability that certain patterns of activity will emerge. These chemical messengers, often called neurotransmitters, are released at synapses when neurons communicate. Once released, they bind to receptors on neighboring cells, altering how those cells respond to incoming signals. Some increase the chance that activity will continue spreading, while others reduce it. This balance allows the brain to remain flexible rather than rigid, responsive rather than fixed. Chemical signaling works over multiple timescales. Some effects are brief, influencing activity for only moments. Others persist longer, shaping patterns across minutes or hours. This layered influence allows the brain to integrate immediate conditions with recent history, creating continuity rather than abrupt change. The system remembers not by storing events, but by adjusting responsiveness. Importantly, chemical signals are not evenly distributed across the brain. Different regions maintain different chemical environments depending on state and context. These environments influence which networks are more active and which remain quiet. The same electrical signal can have different effects depending on the surrounding chemical conditions, allowing context to shape outcome without explicit instruction. Chemical signaling also contributes to coordination across large areas. By diffusing beyond individual synapses, some messengers influence broad regions at once. This allows the brain to shift overall modes of operation smoothly, preparing networks for rest, focus, or integration. These shifts are gradual, reducing instability and supporting balance. From the perspective of the mind, chemical signaling remains invisible. There is no sensation associated with these changes, yet they quietly shape how experience unfolds by influencing which patterns are more likely to arise. The brain does not announce these adjustments. They occur continuously, guided by internal feedback rather than awareness. Understanding chemical signaling helps clarify why the brain is neither purely electrical nor purely structural. Communication depends on both speed and modulation, timing and probability. Electrical activity sets the rhythm, while chemistry shapes the flow. Together, they allow networks to coordinate without central control. As this understanding settles, attention can move gently toward how the brain manages its energy. Communication and regulation require resources, and the brain must balance activity with efficiency. The next step in this exploration lies in examining how the brain uses energy to sustain itself, quietly prioritizing balance over excess as time continues to unfold. The brain operates within strict energetic limits. Although it represents only a small portion of the body by weight, it requires a continuous and reliable supply of energy to sustain its activity. This energy is not used for bursts of effort alone, but for ongoing maintenance, signaling, and regulation. From moment to moment, the brain balances how resources are distributed, ensuring that activity remains possible without excess or depletion. Energy in the brain supports several overlapping processes at once. Neurons must maintain electrical gradients, recycle chemical messengers, and repair cellular components as they wear down. These processes occur continuously, even when no external task is being performed. Rest does not reduce the brain's need for energy. Instead, it changes how that energy is allocated, shifting emphasis from outward response to internal coordination. Because energy is limited, the brain cannot activate all networks at full intensity simultaneously. Instead, it prioritizes. Some networks become more active while others quiet down, allowing resources to be shared efficiently. This prioritization is not decided consciously. It emerges from feedback between activity levels, chemical signals, and available resources. When demand rises in one area, adjustments occur elsewhere to maintain balance. Efficiency is central to this system. Over time, the brain tends to favor patterns of activity that achieve coordination with lower energetic cost. Connections that transmit signals reliably with less effort are strengthened, while inefficient pathways gradually weaken. This process does not aim for speed or power, but for sustainability. The goal is not maximum output, but long-term stability. Energy management also shapes timing. Sustained high activity cannot be maintained indefinitely. Rhythms of activation and rest allow the brain to distribute energy use across time, preventing overload. These rhythms appear at many scales, from brief pauses between signals to longer cycles of activity and rest. Together, they allow the brain to remain responsive without exhausting its resources. Importantly, energy use in the brain is closely tied to prediction. rather than waiting for demands to arise, the brain often prepares in advance, allocating resources based on expected conditions. This anticipatory regulation reduces waste and smooths transitions between states. When expectations are met, energy use remains efficient. When conditions change, adjustments follow. From the perspective of the mind, these energetic processes are not felt directly. There is no awareness of energy being allocated or conserved. Yet these invisible adjustments shape everything the brain does, influencing which patterns are likely to emerge and which remain quiet. Energy management quietly constrains possibility, guiding activity without instruction. Understanding the brain through the lens of energy highlights its practical nature. It is not driven by abstract goals, but by the need to remain viable over time. Every adjustment, every shift in activity, reflects an effort to sustain balance rather than to achieve dominance or control. As this understanding settles, attention can move gently toward how the brain behaves when it is not engaged in specific tasks. Even in apparent stillness, energy continues to flow and activity continues to organize itself. The next step in this exploration lies in examining the brain at rest and how background activity supports continuity without requiring focus or effort. When the brain is not focused on an external task, it does not become inactive. Instead, it shifts into a different mode of organization, often described as resting activity. This state is not a pause or a shutdown. It is a condition in which internal coordination continues without being directed toward immediate goals or responses. From the outside, this may appear quiet. From within the system, activity remains steady and structured. During rest, networks across the brain continue to exchange signals. Electrical rhythms persist, chemical environments adjust, and energy is distributed according to internal priorities rather than external demands. This background activity occupies a significant portion of the brain's overall energy use, reflecting its importance. The brain spends much of its time in this mode, even during waking hours, maintaining continuity beneath moments of focus. Researchers observe that resting activity follows consistent patterns. Certain networks become more prominent, while others reduce their activity. These patterns are not random. They reflect the brain's tendency to organize itself when not constrained by specific tasks. Resting activity allows information to circulate internally, supporting integration across systems without requiring immediate action. Importantly, rest does not mean disengagement from the body. Signals related to breathing, posture, and internal state continue to flow. The brain remains in communication with bodily systems, adjusting regulation as needed. Rest simply shifts the emphasis away from targeted interaction with the environment and toward internal balance. The brain at rest is also sensitive to recent history. Patterns of activity during rest are influenced by what occurred earlier, reflecting learning, emotion, and adaptation. This influence does not appear as replay in a literal sense. Instead, it shapes which networks are more likely to interact, allowing recent experiences to be incorporated gradually without effort. From the perspective of the mind, resting activity is rarely noticed. Attention may drift or settle, but the underlying coordination continues regardless. This invisibility reinforces the idea that much of the brain's work happens outside awareness, supporting stability without drawing focus. Resting activity also provides flexibility. By maintaining a baseline of coordination, the brain can respond smoothly when demands arise. Networks remain loosely connected, ready to strengthen or quiet as needed. This readiness reduces the cost of switching between states, supporting efficiency and continuity. Understanding the brain at rest helps remove the idea that productivity defines function. Even in stillness, the brain is active, maintaining relationships that support long-term balance. Rest is not absence. It is a different configuration of activity, one that allows the system to remain whole. As this understanding settles, attention can move gently toward one of the most studied features of resting activity. The next step in this exploration lies in examining the default mode network, a large-scale pattern that illustrates how the brain organizes itself when attention is not directed outward, quietly sustaining internal coherence over time. Within the brain's resting activity, scientists have identified a large-scale pattern known as the default mode network. This network is not a single structure or location, but a set of regions that tend to become active together when the brain is not engaged in specific tasks. It represents a mode of coordination rather than a function with a clear outcome. The default mode network becomes more prominent when attention is not directed outward. When external demands are low, activity within this network increases, while task-focused networks quiet down. This shift does not indicate disengagement. Instead, it reflects a reorientation from responding to the environment toward maintaining internal coherence. Regions associated with the default mode network are distributed across the brain, spanning areas involved in memory, integration, and long-term regulation. Their coordinated activity suggests that the brain uses periods of rest to maintain continuity across time. Rather than processing immediate input, the network supports internal organization, linking past experience with present conditions. Importantly, the default mode network does not operate continuously or exclusively. It alternates with other networks as demands change. When attention is required, its activity decreases smoothly, allowing task-oriented coordination to take over. This flexibility highlights the brain's ability to shift between modes without disruption, preserving balance across changing conditions. Researchers emphasize that the default mode network should not be understood as a place where specific thoughts occur. It does not generate content in a deliberate way. Instead, it reflects how the brain maintains readiness and integration when not occupied with directed tasks. Activity within the network provides a background structure that supports continuity rather than expression. The presence of the default mode network also illustrates how rest is an active state. Even without external focus, the brain continues to coordinate widely separated regions, sustaining relationships that allow smooth transitions between states. This coordination helps explain why rest supports adaptation and resilience over time. From the perspective of the mind, the activity of the default mode network is not directly experienced. There is no clear signal when it becomes active or quiet. Its influence is subtle, shaping how easily the brain can shift focus or integrate information rather than producing noticeable sensations. Understanding the default mode network reinforces the idea that the brain is never idle. Even in moments of stillness, patterns of coordination persist, supporting continuity without effort. The brain remains engaged in maintaining itself, quietly adjusting relationships that unfold across time. As this understanding settles, attention can move gently toward how memory fits into this ongoing background activity. The next step in this exploration lies in examining memory, not as a stored object, but as a process that emerges from coordination across networks, continuously reshaped as the brain rests and adapts. Memory is often imagined as something the brain stores and retrieves, but science approaches it differently. Rather than existing as fixed records, memories are understood as patterns of activity that are reconstructed each time they are used. These patterns emerge from coordination across networks, shaped by context, timing, and prior activity. Memory, in this sense, is not a place, but an ongoing process. When experiences occur, they influence how networks interact. Connections between neurons may become more likely to activate together, forming tendencies rather than permanent imprints. These tendencies can be strengthened, softened, or reshaped over time. Each recall does not simply access an existing memory. It participates in rebuilding it, allowing the memory to change subtly with each use. This process-based view explains why memory is flexible rather than exact. Details can shift, emotional tone can adjust, and relevance can change as new experiences are integrated. The brain does not aim to preserve perfect accuracy. Instead, it prioritizes coherence and usefulness, allowing memories to remain compatible with current conditions. Stability and adaptability are balanced rather than traded. Memory also unfolds across time. Some changes occur quickly, while others require repeated exposure and rest. Activity during rest and sleep supports this gradual refinement, allowing networks to adjust without interference from immediate demands. Memory becomes distributed across many moments rather than fixed in a single event. Importantly, memory does not operate independently from the rest of the brain. It is influenced by emotion, attention, and bodily state, all of which shape how networks interact. A memory is not a standalone object. It is a pattern embedded within a larger system, sensitive to changes in the surrounding environment. From the perspective of the mind, memory can feel stable, as if something is being recalled intact. Beneath that experience, however, reconstruction is occurring. The sense of continuity arises from consistent coordination rather than static storage. The brain recreates what is needed, when it is needed, using available patterns. Understanding memory as a process removes the pressure to preserve information perfectly. The brain is not designed to archive experiences unchanged. It is designed to integrate them, allowing learning to remain flexible over time. Memory serves adaptation rather than record keeping. As this understanding settles, attention can move gently toward how change itself is supported. The brain must remain capable of adjusting connections without losing coherence. The next step in this exploration lies in examining how short-term and long-term change coexist, and how plasticity allows the brain to adapt gradually across time while maintaining continuity. Change in the brain does not occur all at once. Instead, it unfolds across multiple timescales, allowing adaptation without instability. Some adjustments happen quickly, shaping responses from moment to moment. Others develop slowly, reflecting patterns of activity repeated over days, months, or years. The brain's ability to operate across these timescales is what allows it to remain both responsive and consistent. Short-term change often involves temporary shifts in how networks interact. Chemical signals can alter how easily neurons respond, increasing or decreasing activity for brief periods. These adjustments allow the brain to respond to immediate conditions without permanently altering its structure. Once conditions change, activity can return to previous patterns, preserving flexibility. Long-term change, by contrast, involves gradual modification of connections themselves. When certain patterns of activity recur, the likelihood that those patterns will reappear increases. Connections that are consistently involved in coordination may strengthen, while others weaken through disuse. This process does not require awareness or intention. It reflects the brain's tendency to adapt based on history rather than instruction. Importantly, short-term and long-term changes are not separate systems. They interact continuously. Temporary shifts can create conditions that favor lasting adjustment, while long-term structure influences how short-term responses unfold. This interaction allows the brain to adapt without losing coherence, integrating new information while preserving stability. Plasticity, the brain's capacity for change, is not unlimited. Boundaries exist to prevent excessive instability. Chemical environments, energy availability, and network organization all place constraints on how quickly and how far connections can adjust. These constraints are not limitations, but safeguards, ensuring that adaptation remains proportional and integrated. The brain also distributes change across time to reduce strain. Rather than reorganizing everything at once, it adjusts gradually, allowing new patterns to settle before further modification occurs. This slow pace supports resilience, reducing the risk of disruption. Change becomes a process of accumulation rather than replacement. From the perspective of the mind, these processes are largely invisible. Learning may feel sudden, or understanding may appear to arrive all at once. But beneath that experience lies a gradual reshaping of relationships. The sense of insight reflects the crossing of a threshold, not the sudden creation of structure. Understanding short-term and long-term change together highlights the brain's balance between flexibility and continuity. It adapts without erasing itself, incorporating new patterns into existing frameworks. This balance allows experience to accumulate meaningfully over time. As this understanding settles, attention can move gently toward how learning continues even when awareness is not involved. The brain does not require focus or intention to adjust. The next step in this exploration lies in examining how learning unfolds without awareness, quietly shaping patterns as the system rests and integrates across time. Learning is often associated with effort, repetition, and attention. But much of the brain's adjustment occurs without conscious involvement. Patterns continue to change even when awareness is elsewhere or absent altogether. This form of learning is not deliberate. It emerges naturally as networks interact, shaped by timing, context, and prior activity rather than intention. During waking life, experiences activate certain pathways more than others. These activations leave traces in the form of altered probabilities, making some patterns more likely to occur again. When awareness fades, the brain does not stop working with these patterns. Instead, it continues to adjust relationships quietly, integrating recent activity into its broader structure. Periods of rest and sleep are especially important for this kind of learning. Without the need to respond to immediate demands, networks are free to interact more broadly. Connections can be revisited, strengthened, or softened without interruption. This process does not replay events exactly as they occurred. It reorganizes relationships, allowing general patterns to emerge rather than preserving specific details. Learning without awareness also supports efficiency. By adjusting patterns automatically, the brain reduces the need for repeated effort during waking life. Skills become smoother, responses become more coordinated, and understanding becomes more accessible. These changes feel natural because they unfold gradually, guided by internal regulation rather than conscious practice. Importantly, this form of learning does not require direction from the mind. There is no need to decide what should be learned or remembered. The brain responds to usage. Pathways that are engaged more often are more likely to be refined, while those that are rarely activated gradually fade. This self-organizing process allows learning to reflect real patterns of interaction rather than imposed priorities. Learning without awareness also helps maintain balance. If learning required constant attention, the system would become strained. By distributing adjustment across moments of rest, the brain preserves stability while remaining adaptable. Change becomes part of the background rather than a disruption. This process continues across the lifespan. Even in adulthood, when development slows, learning without awareness supports adaptation to gradual changes in environment and body. The brain remains responsive, adjusting quietly as conditions evolve. Understanding learning without awareness helps reframe how change occurs. It is not always driven by effort or insight. Much of it unfolds beneath awareness, shaped by rhythms of activity and rest. The brain learns because it is active, not because it is instructed. As this understanding settles, attention can move gently toward how emotional signals interact with these learning processes. The next step in this exploration lies in examining how emotion and the brain influence one another as part of ongoing regulation, quietly shaping patterns without requiring conscious involvement. Emotion, from a scientific perspective, is not a separate layer added onto thinking. It is an integral part of how the brain organizes information and regulates behavior. Emotional signals influence attention, memory, and learning, shaping which patterns of activity become more prominent and which fade into the background. These signals operate continuously, whether or not they are noticed. Within the brain, emotion arises from interaction between multiple systems rather than from a single location. Networks involved in evaluation, memory, bodily regulation, and prediction work together to assess significance. This assessment does not require conscious labeling. It reflects how strongly certain signals influence activity across the system. Emotional relevance, in this sense, guides priority rather than producing a feeling to be examined. Emotional signaling also interacts closely with memory. Experiences that carry stronger emotional weight tend to influence how networks adjust over time. Connections associated with these experiences may become more likely to activate together, shaping future responses. This does not mean emotional memories are stored intact. Instead, emotional tone influences how patterns are reorganized, affecting what is emphasized and what is softened as memory is reconstructed. The brain also uses emotional signals to support regulation. Internal states such as arousal, balance, and readiness are monitored continuously. When conditions drift too far in one direction, emotional signaling contributes to adjustment, nudging activity back toward stability. These adjustments occur gradually, without instruction or awareness, helping the system remain within workable limits. Importantly, emotion does not operate independently of learning. Emotional signals influence which patterns are reinforced and which are allowed to fade. Learning becomes more efficient when it aligns with emotional relevance, not because emotion demands attention, but because it shapes probability. Networks that matter for adaptation receive more adjustment over time. From the perspective of the mind, emotion can feel immediate and personal. Beneath that experience, however, lies a distributed process of coordination and regulation. The brain is not reacting emotionally in isolation. It is integrating information across systems to maintain balance and continuity. Understanding emotion as a regulatory signal rather than a separate experience helps reduce the sense that it must be controlled or interpreted. Emotional activity is part of how the brain manages complexity. It contributes to adaptation without requiring conscious oversight. As this understanding settles, attention can move gently toward another core function of the brain. Beyond responding to what has already happened, the brain continuously anticipates what might come next. The next step in this exploration lies in examining prediction and adjustment, and how the brain uses expectation to guide activity quietly across time. A central feature of brain activity is prediction. Rather than reacting only after events occur, the brain continuously anticipates what is likely to happen next. These predictions are not conscious forecasts. They are patterns of expectation shaped by past activity, guiding how networks prepare and adjust before information arrives. Prediction allows the brain to remain efficient, reducing the effort required to respond to familiar situations. Predictions emerge from learned relationships within networks. When certain patterns tend to follow others, the brain becomes more likely to activate those patterns in advance. This preparation does not guarantee an outcome. It simply increases readiness, making coordination smoother when expectations align with reality. When they do not, the brain adjusts, updating relationships gradually rather than resetting entirely. Adjustment is a quiet process. When incoming signals differ from expectation, activity shifts to reduce the mismatch. This shift does not require awareness. Chemical signaling, timing changes, and network interaction all contribute to recalibration. Over time, these small adjustments refine prediction, improving alignment without demanding attention. Importantly, prediction operates across multiple timescales. Some expectations last only moments, shaping immediate responses. Others persist longer, reflecting stable features of the environment or body. The brain balances these layers, allowing short-term flexibility within long-term continuity. This balance supports adaptation without instability. Prediction also conserves energy. Preparing for likely outcomes reduces the cost of sudden change. When expectations are accurate, activity flows smoothly with minimal adjustment. When conditions shift, the brain adapts, but within bounds that preserve overall stability. This efficiency reflects the brain's preference for sustainability over precision. From the perspective of the mind, prediction is largely invisible. Experience often feels reactive, as if responses arise only after events occur. Beneath that experience, anticipation has already shaped activity, guiding attention, learning, and regulation. The sense of immediacy arises from coordination rather than surprise. Understanding prediction and adjustment helps clarify how the brain maintains continuity. It does not wait passively for information. It participates actively, shaping its own readiness through expectation. This participation allows the system to remain aligned with a changing world without becoming overwhelmed. As this understanding settles, attention can move gently toward how prediction interacts with the body. The brain does not operate in isolation. Its expectations extend into physiological regulation, shaping movement, balance, and internal state. The next step in this exploration lies in examining how the brain and body coordinate, forming a unified system that adjusts quietly across time. The brain does not function apart from the body. It is embedded within a continuous exchange of signals that move in both directions, forming a unified system rather than a hierarchy. Information flows inward from the body and outward from the brain, at all times, shaping regulation, movement, and balance, without requiring awareness or command. Signals from the body provide constant feedback. Changes in posture, breathing, temperature, and internal chemistry are communicated to the brain through sensory pathways that operate quietly in the background. These signals do not announce themselves. They influence activity subtly, adjusting how networks coordinate based on the body's current state. The brain responds by modifying its patterns, maintaining stability, rather than issuing instructions. At the same time, the brain influences the body through distributed control rather than direct orders. Instead of commanding specific outcomes, it adjusts probabilities. Muscles become more or less likely to activate. Organs shift their rhythm slightly. Internal systems coordinate through feedback loops that allow fine-tuned adjustment rather than rigid control. This approach supports flexibility, allowing the body to respond smoothly to changing conditions. This two-way exchange blurs the distinction between brain and body. Regulation emerges from interaction rather than dominance. The brain does not stand above the body directing it. It participates within the system, responding to signals as much as it sends them. Balance arises from this mutual influence, not from centralized authority. Energy and timing play important roles in this coordination. The brain must account for the body's limits, adjusting activity to match available resources. When energy is low, activity patterns shift to conserve. When readiness increases, coordination becomes more responsive. These adjustments occur automatically, guided by ongoing feedback rather than awareness. Movement illustrates this relationship clearly. Actions are not produced by a single decision followed by execution. They emerge from coordination across sensory input, prediction, and muscle readiness. The brain prepares possibilities, the body provides feedback, and movement unfolds as a negotiated outcome. This process feels seamless from the perspective of the mind because coordination occurs beneath awareness. Internal regulation follows a similar pattern. Breathing, heart rhythm, and digestion are adjusted continuously in response to changing conditions. The brain participates in these adjustments, but it does not monitor them consciously. Regulation is distributed across networks that integrate bodily signals into ongoing activity, preserving stability without effort. Understanding the brain and body as a single coordinated system helps remove the sense that either must be controlled. Neither operates independently. Each responds to the other, forming a continuous loop of adjustment. This loop allows both to remain adaptable while maintaining continuity over time. As this understanding settles, attention can move gently toward how the brain relates to time itself. Beyond immediate coordination, the brain operates across layers of time, integrating moments, hours, and years into a coherent flow. The next step in this exploration lies in examining how the brain processes time and how this temporal coordination supports continuity across the lifespan. The brain does not operate within a single moment. Instead, it coordinates activity across many layers of time at once. Some processes unfold in fractions of a second, while others reflect patterns shaped over years or decades. These layers coexist, allowing the brain to respond quickly while maintaining long-term continuity. Time, in this sense, is not a backdrop. It is an active dimension of regulation. At the shortest timescales, electrical signals move rapidly between neurons, allowing immediate coordination. These fast processes support moment-to-moment adjustment, enabling networks to align their activity with changing conditions. At the same time, slower chemical processes shape responsiveness over longer intervals, influencing how patterns evolve across minutes or hours. Together, these layers allow the brain to remain flexible without losing coherence. Beyond these immediate scales, the brain also integrates history. Past activity influences present coordination through altered probabilities and strengthened relationships. This influence does not appear as a record of events. Instead, it shapes how the brain expects patterns to unfold. The present is continuously informed by the past, even when that past is not recalled or recognized. The brain also anticipates the future. Prediction extends activity forward in time, preparing networks for what is likely to occur. This preparation reduces the need for abrupt change, smoothing transitions between states. Time, from the brain's perspective, is not divided into past, present, and future. These dimensions overlap, guiding activity simultaneously. Sleep and rest play a crucial role in temporal integration. During periods when external demands are reduced, the brain can adjust relationships across longer timescales. Patterns that form during waking life are revisited and reorganized, allowing gradual refinement. This process helps maintain continuity, ensuring that change unfolds without fragmentation. Importantly, the brain's relationship with time does not require awareness. The mind may experience time as passing slowly or quickly, but beneath that experience, regulation continues steadily. The brain tracks intervals, rhythms, and durations automatically, coordinating activity without conscious reference. Aging illustrates how temporal integration operates across decades. The brain does not replace itself at each stage of life. Instead, it adapts, carrying forward prior organization while incorporating new conditions. This continuity allows identity and function to persist, even as structure and emphasis change. Understanding the brain and time together helps clarify how stability emerges. The brain does not reset with each moment. It weaves moments together, creating a continuous thread of activity that stretches across life. This thread allows experience to feel connected rather than disjointed, even though the underlying system is always changing. As this understanding settles, attention can move gently toward how the brain maintains this continuity through change. The next step in this exploration lies in examining how stability is preserved, even as the brain adapts, revealing how coherence arises from constant adjustment rather than fixed structure. Although the brain is constantly adjusting, it does not drift aimlessly. Stability is preserved even as change continues, allowing function and identity to remain coherent across time. This stability does not come from freezing structure or resisting variation. Instead, it emerges from continuous adjustment that keeps activity within workable ranges. Change in the brain is selective rather than uniform. Some connections are modified frequently, while others remain relatively stable. This uneven distribution allows core patterns to persist, while flexibility is applied where it is most useful. The brain does not rebuild itself entirely in response to new conditions. It layers change onto existing organization, preserving continuity while allowing adaptation. Feedback plays a central role in maintaining this balance. When activity becomes too intense or too weak, regulatory signals adjust responsiveness. Chemical environments shift, timing changes, and network interactions are reshaped just enough to restore equilibrium. These adjustments happen gradually, preventing abrupt transitions that could destabilize coordination. Stability is also supported by redundancy. Multiple pathways can support similar functions, allowing the system to remain effective even when individual connections change. This redundancy does not create inefficiency. Instead, it provides flexibility, enabling the brain to adapt without losing overall capacity. When one route becomes less active, others can compensate. Importantly, stability does not imply sameness. The brain's patterns evolve, reflecting new experiences and conditions. What remains stable is the ability to coordinate, integrate, and regulate. The details shift, but the underlying process continues. From the perspective of the mind, this creates a sense of continuity, even as change unfolds beneath awareness. Time smooths this process. Adjustments made gradually are less disruptive than sudden shifts. By distributing change across repeated cycles of activity and rest, the brain ensures that adaptation remains proportional. Sleep, rest, and recurring rhythms provide opportunities for integration, allowing new patterns to settle without overwhelming existing structure. The brain's ability to maintain stability through change reflects a broader principle of living systems. Survival depends not on resisting variation, but on responding to it in measured ways. The brain exemplifies this principle by remaining flexible while preserving coherence, adapting without losing itself. Understanding stability through change helps clarify why the brain does not need to be controlled. Regulation emerges from interaction rather than instruction. Balance is maintained not by holding still, but by moving continuously within bounds. As this understanding settles, attention can move gently toward how this balance plays out across the lifespan. The next step in this exploration lies in examining how the brain changes from early development through later life, and how stability is preserved even as emphasis and organization shift over decades. The brain does not remain static as time passes. From early development through later life, it changes gradually, adjusting structure, emphasis, and coordination in response to shifting needs. These changes are not abrupt transitions from one state to another. They unfold continuously, allowing stability to be preserved even as organization evolves. In early life, the brain is characterized by rapid growth and high flexibility. Connections form quickly, and activity patterns adjust easily in response to experience. During this period, the brain prioritizes exploration and broad integration, allowing a wide range of patterns to emerge. This flexibility supports learning and adaptation as the system establishes its foundational organization. As development progresses, change becomes more selective. Rather than forming new connections indiscriminately, the brain refines existing networks. Patterns that prove useful are strengthened, while others are softened. This refinement supports efficiency. allowing coordination to occur with less effort over time. The brain becomes more stable, not because it stops changing, but because it learns which changes to preserve. In adulthood, the balance between stability and adaptability continues. The brain remains capable of learning and adjustment, but change unfolds more gradually. This pace reflects accumulated structure. New patterns must integrate with existing organization rather than replacing it. Adaptation becomes layered, allowing continuity of function even as conditions shift. Later in life, changes in the brain reflect shifting priorities rather than loss of purpose. Energy allocation, chemical balance, and timing may adjust, influencing how networks coordinate. These adjustments do not erase prior organization. Instead, they reshape emphasis, allowing the system to remain functional within new constraints. The brain continues to regulate itself, adapting to gradual physiological changes. Importantly, variation across individuals increases with age. No two brains follow identical trajectories. Genetics, environment, and long-term experience all influence how change unfolds. This diversity highlights the adaptability of the system. Stability does not require uniformity. It emerges through personalized adjustment rather than fixed rules. Across the lifespan, continuity is preserved through relationship rather than repetition. The brain does not reset itself at each stage. It carries forward its history, integrating new conditions into an evolving structure. This process allows identity and function to remain connected over time, even as the details shift. From the perspective of the mind, these changes often go unnoticed. Experience feels continuous, even though the underlying system is adapting. This sense of continuity arises because regulation remains intact. The brain adjusts in ways that preserve coherence rather than drawing attention to change. Understanding the brain across the lifespan reveals adaptation as a quiet, ongoing process. Change does not threaten stability when it is integrated gradually. Instead, it sustains it, allowing the brain to remain responsive while maintaining continuity across the full span of life. As this understanding settles, attention can move gently toward the differences between individual brains. The next step in this exploration lies in examining variation and how diversity in structure and activity reflects the brain's capacity to adapt uniquely while following shared biological principles. No two brains are organized in exactly the same way. Even though they follow shared biological principles, variation is a fundamental feature rather than an exception. Differences in structure, timing, chemistry, and connectivity arise naturally through genetics, development, experience, and environment. This diversity does not represent deviation from a standard. It reflects the brain's capacity to adapt uniquely while maintaining overall function. Variation begins early. From the earliest stages of development, small differences in growth and signaling influence how networks form. As experiences accumulate, these differences widen. Patterns that are used more frequently become more established, while others recede. Over time, each brain develops a distinctive balance of stability and flexibility, shaped by its history rather than by a fixed template. Importantly, variation does not imply inequality of function. Brains can arrive at similar outcomes through different configurations. Multiple network arrangements can support effective coordination, allowing the system to achieve balance in diverse ways. This redundancy highlights the brain's resilience. Function is not tied to a single structure, but to the relationships between components. Chemical environments also contribute to variation. Differences in signaling dynamics influence how networks respond to input and adjust over time. These differences shape timing, sensitivity, and regulation without determining specific outcomes. Variation in chemistry supports adaptability, allowing brains to respond to similar conditions in slightly different ways. Environmental factors play a continuing role. Long-term patterns of activity, rest, learning, and stress influence how networks are maintained. These influences do not override biological structure. They interact with it, shaping emphasis rather than replacing organization. The brain remains responsive to context across the lifespan, integrating external conditions into its ongoing regulation. From the perspective of the mind, variation can feel like personality or preference. Beneath that experience lies a complex pattern of distributed differences that influence coordination. There is no single source of individuality. It emerges from interaction across systems rather than from a central location. Understanding variation between brains helps shift focus away from comparison and toward appreciation of diversity. There is no ideal configuration toward which all brains converge. Stability and effectiveness arise through different pathways, each reflecting a unique balance of structure and experience. As this understanding settles, attention can move gently toward an important implication of this diversity. If function is distributed and variable, then no single place within the brain contains thought or identity. The next step in this exploration lies in examining how the brain operates without a central location of control, reinforcing the idea that coordination arises from interaction rather than command. Although the brain is often described as having parts that do specific jobs, science shows that no single location contains thought, awareness, or identity. There is no central room where experience gathers, and no command center issuing instructions to the rest of the system. Instead, function emerges from interaction, shaped by coordination across many regions, working together over time. When activity is measured across the brain, it becomes clear that similar functions can involve different areas depending on context. A process that appears in one network under certain conditions may involve a different configuration under others. This flexibility reflects the brain's distributed organization. Meaning does not reside in a place. It arises from patterns of relationship. Even processes that feel unified from the perspective of the mind are supported by many systems acting together. Sensory input, memory, prediction, and regulation all contribute simultaneously. No single region creates the experience. It is assembled through timing, interaction, and feedback across networks that span the brain. This lack of centralization increases resilience. When one area changes or becomes less active, other pathways can adapt to maintain coordination. The brain does not depend on a single structure for continuity. Instead, it relies on overlapping networks that can reorganize as needed. Stability is preserved through redundancy and flexibility, rather than rigid control. Distributed organization also allows the brain to scale across time and demand. During focused activity, certain networks may become more tightly coordinated. During rest, coordination spreads more broadly. These shifts do not require a supervisor. They emerge naturally as activity patterns adjust in response to context. From the perspective of the mind, it can feel as though there is a single observer behind experience. Neuroscience suggests otherwise. The sense of unity arises not from a central entity, but from coherent coordination across systems. When timing and interaction align, experience feels whole, even though it is distributed. Understanding that the brain is not centralized helps dissolve the idea that it must be managed or optimized from a single point. There is no place to control because control is not how the system operates. Regulation arises from interaction, guided by feedback rather than instruction. As this understanding settles, attention can move gently toward a more abstract view. If the brain is not a collection of parts, but a pattern of activity, then it can be understood as rhythm rather than structure. The next step in this exploration lies in viewing the brain as an ongoing rhythm, one that continues quietly, whether or not it is observed, carrying the night forward without effort. When the brain is viewed not as a structure, but as ongoing activity, a different picture begins to emerge. Rather than a collection of parts performing tasks, the brain can be understood as rhythm. Activity rises and falls, coordination tightens and loosens, and patterns repeat with gentle variation across time. Nothing holds still, yet continuity remains. These rhythms exist at many levels at once. Electrical activity fluctuates in repeating patterns. Chemical signaling waxes and wanes. Networks assemble and dissolve. Some rhythms unfold quickly, while others stretch across hours or days. Together, they form a layered flow that supports coordination without requiring direction. Rhythm allows the brain to manage complexity. Instead of processing everything at once, activity is distributed across time. Certain processes come forward while others recede, making room for balance. This ebb and flow prevents overload, allowing the system to remain responsive without becoming strained. Regulation becomes a matter of timing rather than control. Importantly, rhythm does not imply repetition without change. Each cycle is shaped by what came before. Small differences accumulate, allowing adaptation to occur gradually. The brain repeats its patterns, but never in exactly the same way. This subtle variation allows learning and integration to continue without disrupting stability. From the perspective of the mind, these rhythms are rarely noticed. Experience may feel continuous or fragmented, fast or slow, but beneath those impressions lies steady coordination. The brain does not announce its rhythms. They operate quietly, supporting coherence regardless of awareness. Viewing the brain as rhythm also helps dissolve the sense that it must reach an endpoint. There is no final state toward which activity moves. Instead, the brain continues cycling, adjusting and maintaining itself as long as conditions allow. Function is sustained through movement, not through arrival. This rhythmic perspective aligns with how living systems persist. Life does not hold a pose. It flows, adapting through repetition and variation. The brain exemplifies this principle, remaining active and integrated by cycling through patterns rather than fixing itself in place. As this understanding settles, the emphasis on explanation can begin to soften. Details matter less as the broader flow becomes clearer. The next step in this exploration lies in allowing those details to loosen, letting structure fade gently into background awareness, as attention drifts further from analysis and closer to rest. As this exploration continues, the focus can begin to soften. The specific details of structure, signaling, and coordination no longer need to be held in place. What remains is a broader sense of flow, an understanding that the brain continues through rhythm and relationship, rather than through effort or direction. The system does not require constant explanation in order to function. At this point, it becomes clear that much of what the brain does happens beyond the reach of description. Processes overlap, influence one another, and fade into the background as new patterns emerge. Trying to isolate any single element becomes less useful. The brain is not experienced as a list of parts, but as continuity unfolding through time. Letting the details loosen does not mean they disappear. Instead, they settle into a quieter layer of understanding. The knowledge that communication, regulation, and adaptation are ongoing can remain present without being examined. The brain continues its work, whether or not it is being named, measured, or followed. This softening mirrors how the brain itself operates during rest. Activity does not stop, but emphasis shifts. Networks interact more broadly. Boundaries blur. Coordination becomes less about precision and more about balance. The system moves toward integration rather than focus, allowing change to settle gently into existing patterns. From the perspective of the mind, this can feel like a gradual release. Thoughts may become less defined. Attention may drift without direction. This is not a loss of clarity, but a different mode of organization. The brain is still active, still coordinated, simply operating without the need for narrow focus. There is no need to remember what came before. The brain does not require a summary in order to continue. Each moment carries forward what it needs automatically, shaped by rhythms that persist beneath awareness. The continuity of activity does not depend on conscious tracking. As details fade, the sense of effort fades with them. The brain is not waiting for instruction or conclusion. It continues through repetition and variation, guided by patterns older than thought. This ongoing motion supports rest rather than interrupting it. In this quieter space, understanding becomes less about content and more about atmosphere. The idea of the brain as a living rhythm can remain in the background, steady and unhurried, as attention loosens its grip on explanation. From here, the path continues gently toward rest itself. The next step does not require learning anything new. It simply involves recognizing that the brain continues without supervision, maintaining its balance as the night carries on, allowing rest to deepen naturally without effort or expectation. As the night deepens, it becomes easier to recognize that the brain does not depend on attention to continue its work. Long before awareness arose, these systems were already operating, maintaining balance through coordination rather than oversight. Attention is something the brain produces, not something it requires in order to function. Even when focus dissolves, activity remains organized. Signals continue to flow. Networks continue to adjust. Rhythms rise and fall in familiar patterns, guided by timing and feedback rather than intention. The absence of attention does not interrupt these processes. In many cases, it allows them to unfold more freely. This is especially true during periods of rest and sleep. As external demands fade, the brain shifts further inward, prioritizing integration over response. Coordination becomes broader and less constrained. Patterns formed during waking life are revisited and softened, allowing adjustment to occur without pressure. The system does not hurry. It follows its own pace. From the perspective of the mind, this can feel like drifting. Thoughts may appear briefly and then fade. Sensations may blur. The sense of directing experience loosens. Beneath this experience, however, regulation remains intact. The brain continues to manage timing, energy, and balance without drawing attention to itself. The fact that the brain continues without attention is not a sign of neglect. It is a sign of reliability. Living systems persist by distributing responsibility across interaction rather than concentrating it in awareness. The brain exemplifies this principle by remaining functional regardless of where attention rests. This autonomy supports rest. When attention is no longer needed to guide activity, effort dissolves. There is nothing to maintain and nothing to track. The brain carries forward what it needs automatically, guided by rhythms that have repeated countless times before. Understanding this can bring a sense of ease. There is no need to hold the night together. The system already knows how to continue. Each moment flows into the next without requiring participation. The brain adjusts, integrates, and settles on its own. As this recognition settles, the final movement of this journey begins to take shape. The emphasis shifts fully away from explanation and toward rest. The next section does not introduce new ideas. It simply allows everything already present to quiet further, as the brain rests within its own ongoing process, steady and unhurried, as the night continues. When activity continues to soften, the brain enters a mode where integration becomes more important than distinction. Networks that were once discussed separately no longer need to be held apart. Communication blends. Boundaries loosen. The system shifts away from organizing details and toward maintaining coherence across the whole. Integration does not require effort. It emerges naturally when competing demands fall away. Without the need to respond outwardly, the brain allows signals to circulate more freely, linking regions that may not interact as directly during focused activity. This circulation does not aim toward a conclusion. It supports balance, smoothing differences rather than sharpening them. During these periods, timing becomes more fluid. Rhythms still exist, but they overlap gently, no longer needing strict alignment. Electrical activity slows and spreads. Chemical environments stabilize. The system favors continuity over change, allowing recent adjustments to settle into place without pressure. This integrative state is not passive. It is quietly active, maintaining the relationships that allow the brain to remain whole. Patterns shaped by earlier experience are revisited, not to be evaluated, but to be absorbed. What fits remains. What does not gradually fades. The process is gradual, guided by repetition rather than decision. From the perspective of the mind, this integration often goes unnoticed. There is no clear signal that it is happening. Awareness may drift, fragment, or dissolve altogether. Beneath that experience, coordination continues uninterrupted, guided by rhythms that do not require observation. Integration also protects stability. By distributing adjustment across many networks at once, the brain avoids concentrating change in any single area. This diffusion allows adaptation to occur without disruption. The system remains flexible while preserving continuity. Understanding this integrative phase helps clarify why rest feels restorative without effort. The brain does not need to fix itself. It only needs time in a state where coordination can spread and settle naturally. Given space, the system organizes itself quietly. As this integration deepens, activity begins to simplify further, not by stopping, but by becoming less differentiated. The next movement in this journey lies in allowing this simplification to continue as the brain settles into an even quieter mode of coordination, steady and unhurried. As the night continues, brain activity does not disappear. It recedes into the background, becoming less distinct and less demanding. Signals still move. Networks still coordinate, but nothing rises sharply enough to claim attention. The system shifts toward maintenance rather than modulation. In this state, change slows. Adjustments become smaller, spread across longer intervals. Rhythms stretch and soften, favoring consistency over responsiveness. The brain remains active, but its activity is no longer oriented toward adaptation. It is oriented toward preservation. This background mode allows the system to remain stable without intervention. There is no need to evaluate or respond. Activity flows according to established patterns, guided by timing rather than novelty. The brain relies on repetition, not exploration, allowing everything to settle. From the perspective of the mind, this can feel like fading rather than resting. Thoughts may lose shape. Awareness may thin. There is no need to follow this experience or make sense of it. The absence of clarity does not indicate loss. It indicates transition. Importantly, nothing essential is lost in this state. Regulation continues. Balance is maintained. The brain does not forget how to function when awareness quiets. In fact, this quieting allows regulation to proceed with less interference. This background activity has carried the brain through countless nights. It is familiar, reliable, and self-sustaining. There is no urgency and no destination. The system simply continues, moment by moment, guided by rhythms that no longer need to adjust. As activity settles further into the background, the need for structure dissolves. Explanation becomes unnecessary. What remains is continuity itself, unfolding without effort. As this long, quiet journey settles, there is nothing left to hold in place. The ideas about the brain, its rhythms, its coordination, and its quiet persistence can soften now, drifting gently out of focus. Understanding is no longer needed. The system does not rely on being followed or remembered in order to continue. It simply does what it has always done, moment by moment, without effort. The brain remains active, but its activity no longer needs structure or explanation. Signals continue to move. Rhythms continue to rise and fall. Networks remain gently aligned, maintaining balance through repetition rather than adjustment. Nothing is being solved. Nothing is being improved. Everything is simply continuing. Rest does not arrive as an event. It emerges gradually as attention loosens its grip. Thoughts may appear briefly and dissolve before taking shape. Sensations may blur and fade into the background. The sense of directing experience grows quieter, not because something is ending, but because nothing more is required. From the perspective of the mind, this can feel like drifting without direction. That drifting is not a loss of control. It is the absence of a need for control. The brain does not require supervision to remain steady. It has carried itself through countless nights before this one, guided by rhythms that do not need awareness to exist. Breath follows breath without being counted. Moments pass without being marked. The night unfolds at its own pace, unhurried and indifferent to outcome. The brain continues its quiet work beneath it all, integrating, balancing, and sustaining itself in ways that do not announce themselves. There is comfort in knowing that nothing must be done next. No conclusion needs to be reached. No insight needs to land. The systems that support rest are already in motion, responding to the absence of demand by settling further into stability. If awareness fades, that is welcome. If it lingers softly, that is fine too. The brain adapts to both with equal ease. It does not measure success by depth of sleep or clarity of thought. It simply continues, guided by timing and balance rather than intention. As the night deepens, you are free to let go completely. The science can rest. Curiosity can quiet. The brain carries on without effort, steady and reliable, as it always has. Thank you for spending this time here. Sleep well.